In today's video, we're going to talk about a magnetically separable carbon catalyst for the generation of biojet fuel. As we know, fossil fuels are coming to a depletion. Thus, we need innovative renewable fuels solutions to overcome this problem. In this case, we will be using palm kernel oil as our renewable fuel source, as it has an ideal jet fuel feedstock range and does not compete with the food industry. Palm kernel oil are rich in C12, C14, and C16 fatty acids, which will undergo deoxygenation to produce C11, C13, and C15 hydrocarbon chains. This deoxygenation method is derived of decarboxylation and decarbonylation. The catalyst that we will be using in this study is a magnetically separable catalyst derived of Fe and MO as our active metals and bamboo activated carbon as our catalyst support. The reason why Fe and MO are used is because Fe and MO have been proven to enhance deoxygenation activity, and activated carbon possesses high pore volume and surface area, and it is magnetically stable at high reaction temperatures. Moving on to the research methodology. Firstly, the magnetically recoverable FeMO supported on bamboo catalyst is synthesized via co-precipitation method. The bamboo activated carbon is functionalized with KOH and HCl and then co-precipitated with our active metals, which are Fe and MO, and after that calcined at 530 degrees Celsius. Catalysts with different active metal and support weightage are synthesized to find out which is the most viable for deoxygenation reactions. All catalysts are screened using XRD, BET, VSEM, TPDNH3, TGA, and VSM. This diagram shows the setup of our deoxygenation reaction. From our XRD, we can see the detection of magnetite species, which is our Fe3O4. FeMO peaks shows the presence of bimetallic metal phase. For FeMO supported on activated carbon, we can see that the intense carbon peak is visible, and also the presence of bimetallic FeMO. Also do note that the crystallic size of Fe3O4 reduced when we add activated carbon. This is most likely due to the high dispersion of active metals on activated carbon, which results in the reduce of crystallic size. For the VSM analysis, Fe3O4 magnetite shows the highest intensity. However, hysteresis is also the largest, showing signs of ferromagnetism. For other catalysts such as FeMO and Fe2MO supported on activated carbon shows the slightest signs of paramagnetism, where it shows lower saturation than that of a ferromagnetic. From GCMS graph, we can say that magnetite is not effective for DO activity, thus it is only useful for separation. However, when added with MO, catalytic activity increases. Generally, all metal support catalyst is effective for DO, but different metal gives different hydrocarbon yield and jet fuel selectivity. However, we can see also that Fe and MO in excess is not good for DO reaction. According to former studies, strong acidic sites will enhance DO reaction. However, excessive acidic sites will lead to unwanted reactions known as cracking. This graph also shows that it is in accordance to the GCFID findings where production of hydrocarbon is tallied. From the graph, we can see that there are various oxygenate species produced from this deoxygenation reaction. For pure magnetite, it does not have any hydrocarbon product. However, it produces intermediate products, mainly ketone, and has been proven by previous studies. From the hydrocarbon distribution graph, we can see that catalyst FeMO supported on activated carbon possesses the highest percentage of deoxygenation. We can say that the reason of deoxygenation effectiveness owes to the large surface area of the MEMO supported on activated carbon catalyst. Note that pure magnetite catalyst only possesses of a surface area of 165 meter square per grams, whereas the surface area for FEMO supported on activated carbon reaches up to 1700 meter square per gram. In terms of catalyst acidity, Fe3O4 magnetite and FeMO bimetallic showed medium acidic strength. However, when supported on activated carbon, it shows an increment in acidic strength and acidic density. This is due to the treatment of activated carbon with HCl. High acidic strength of catalyst favors more to DO reaction, which renders selectivity towards hydrocarbon formations. Now, after identifying the most suitable ratio of catalyst, we compared it to its commercial counterpart. FEMO supported on activated carbon shows a lower magnetic saturation, however has a smaller hysteresis than the commercial counterpart, which indicates that FEMOAC is more ferromagnetic than the commercial catalyst. In terms of surface area, the commercial FEMO supported on AC has a higher surface area, but possesses comparable pore size. In terms of catalytic activity, both catalysts exhibited similar BJF fraction trends, but overall, FEMO supported on AC has a higher hydrocarbon yield, more than the commercial counterpart. Based on CHNOS studies, biojet fuel produced showed a lower oxygenate species, which can be comparable to Jet A1 standard fuel. Deactivation kinetics is also studied to determine the cause of deactivation of FEMO supported on activated carbon catalysts. From the deactivation kinetics study, we can identify that the deactivation of catalyst is due to coking. So to summarize our findings, highly thermally stable magnetic FEMO supported on activated carbon catalyst is an effective deoxygenation catalyst. Also, the acidity of catalyst plays a more important role than surface area in deoxygenation reactions. And lastly, we identified that coking is the main deactivation reason for our catalyst. Thank you very much for your attention. Do feel free to contact me for further inquiries.